Ladies and gentlemen, being around for about 40 years was in the PCIM show, and it's my pleasure after all the years continuing supporting SiC and GaN, the wide bandgap devices. We are here to get highlights from the top level of industry, and we are now have a go. The first is Evangelos Theodossiu from Vincotech. Here he is on stage.
Yes. Thanks, Bodo. Thank you for enjoying this panel discussion. Silicon carbide power module design, what does it matter? The implementation of silicon carbide technology was mainly achieved by using existing well-proved and field-tested housing and interconnection technologies based on silicon components. So this was for sure the fastest approach to series introduction of silicon carbide power modules. Since we are talking about silicon carbide design, and as Vincotech is a chip-independent power supply manufacturer, I would like today to discuss with you two aspects which have to be considered and matters while designing a good silicon carbide power module. The first one is the silicon carbide device performance understanding. The second one is the optimal layout design and pin arrangement. So nowadays we see an increasing number of silicon carbide suppliers offering a broad portfolio of silicon carbide devices with different structures and specifications. So the deep understanding of the characteristic figures is crucial for the optimal selection for the right application. On the other hand, to achieve a high power density silicon carbide power modules, in most of the cases, a huge number of silicon carbide devices are used in parallel. In this case, it is important to have a design, a very symmetrical design for the chip and also for the pin arrangement, to have, in the end of the day, a good power module efficiency. Let's deep a little bit more in detail and do these two aspects, and let's start with the silicon carbide device performance. So as we know, the silicon carbide MOSFET has a positive temperature coefficient. So, and the knowledge of the earliest zone at operating temperature, let's say at 120 degrees, is key. Looking here on the left graph, we see we have a huge variation among different silicon carbide devices and suppliers. Dependency of the RDS zone versus the operation temperature. As an example, knowing that supplier D, for instance, showing the best class RDS, the temperature dependency, then you can select this supplier or this device for a good fit of a soft switching application, for instance, or maybe also for hard switching, but for a lower switching frequencies. Also important to know the trade-off between the conduction and switching losses. As we know here in this graph, this is the trade-off between conduction and switching losses. So let's, and this knowledge is also important to have to make a good selection according to the application-specific target. Assuming the target specification target is to have the best compromise between switching and conduction losses, then for sure this supplier A will be the choice. Going now to the layout design. We took here as a test vehicle the Vincotech Flow Dual E3 silicon carbide, which is a 2 million half-bridge module using parallel silicon carbide devices in a industry standard pinout arrangement. On the left side, we see a benchmark of the current density simulation between this standard pinout and optimized layout or pinout in terms of symmetry. And as we can see here, for the standard design, we have a more or less inhomogeneous current density for the inner chips and the loop inductance of 4.3, which is very good for this for the silicon carbide. But with the optimized layout in terms of symmetry, you can even go down up to 1.6, and you have a more homogeneous current density distribution. This can be, as a result, this can be used if you look at an overshoot of at turn-off, then you can reduce the peak voltage up to 30%, which can lead you to reduce further the total losses, and also use it either reduction of the losses or more margin to breakdown. So presenting you these two aspects, I would like to summarize now for the silicon carbide power module design. So among other things, for sure, what is optimal, what you have to consider to achieve a good silicon carbide power module with a good performance is, for sure, you need this excellent know-how of the silicon carbide device performance, and also you need a very symmetrical, optimal layout and pinna arrangement for the loss and inductance. So what next? I think even if the race of the silicon carbide power modules just begun, the next wideband gap is in the starting blocks, and bring with it more new challenges that has to be addressed in terms of design, power module design. And we as a Vincotech, we have already started to address these challenges with our new fast-spec 1 gallium nitride module that you can, of course, join us in our booth and have more details about it. Thanks a lot for this quick overview.
Thank you, Evangelos. It's up to Eugen for the next session. Questions will be answered at the end if we have time left, or we need to look to contact the individual speakers at their booth. It's very comprehensive what we are here doing, but we hope to get you the latest information, which is top on the hill. Eugen, it's your turn.
Konnichiwa, and welcome to short introduction from Mitsubishi Electric. My name is Eugen Stumpf, and the topic is silicon carbide, where to go. This is a statement, this is not a question, because way where to go is clear. First of all, we have to reduce cost. And second, we have to talk about reliability, because the second topic about reliability is today the main hesitation factor for using of silicon carbide. The huge contribution for cost decrease will be switch or transition from 6-inch towards 8-inch, and we're quite confident that we will finish this transition by end of 2025. It is next year. Additionally, this slide depicted where we will go for the high voltage devices. High voltage devices for us is 3.3, 4.5, 6.5, but also we will probably go to 10 kilovolt or 13 kilovolt. Here we will like to keep planar technology, but for power devices with lower blocking voltage capability, like 1200 volt, 650 volt, just like automotive application, we would like to switch to trench structure. Let's talk about reliability. I think the purchasing approach to select power device just based on RDS-on, just based on performance and price, it is quite simple, it's quite primitive approach, and should be considered with a big question mark. We have to talk about 6 topics here. First topic is dependency of on resistance at high temperature. I think it was mentioned already by Mr. Vincotech. Second topic is thermal resistance. It is reflected to how big is a chip size. We shall talk about RB-SOI. We shall talk about robustness of switching SOI. That will be reflected of a selection of RG. How small will be RG, and how quick, how fast we will turn off MOSFET. Number 4, gate switching instability. We're talking here about moving of a characteristic of silicon carbide MOSFET, like threshold voltage, like RDS-on. I would like to talk about this later. We shall talk about die of the distribution die within one lot. And for sure, we shall talk about aging process during causing by bipolar current flowing through the body diode. All 6 topics will reflect or will be considered in the cost structure. Today, let me concentrate on number 4 and number 6, on gate switching instability and body diode current capability. For sure, threshold voltage movement during operation is depend on number of switching events during the lifetime. But how big is this shift? It is depicted on the right side. It is about 0.3 volt, considering 20 years operation with 12-hour operation per day, what is will reflect a solar application, photovoltaic operation. We talk here about 0.3 volt. We don't talk about 1 volt, 3 volt, 5 volt, or 10 volt. And in my opinion, it is today acceptable and can be used. One remarkable point is that our test is done with a switching frequency of 100 kilohertz, what is a lot. Next point is bipolar degradation causing by current through the body diode. How to avoid this degradation? It is simple to avoid this current. How to avoid this current? To implement anti-parallel diode. For sure, that will affect the cost of module, but how to decrease this cost? The solution is to implement or embed this diode into the MOSFET structure, and we did it already with first 3.3 kilovolt devices. These devices is available. It is highlighted in our booth, and welcome to discuss about this Mitsubishi electric approach. How to proceed, how to do next step? In my opinion, we have to talk more honestly and more openly about today's done step and what to do, what is still to do, which questions are still in our brains in order to sleep well if we will apply silicon carbide into the field, if we will go into the field. In my honest opinion, the best location for this discussion is a brewery, because we have to discuss more openly without any compliance topics, without any compliance officer. And I would like to welcome you to visit Düsseldorf, representing 5 breweries. It is about dark beer, it is about alt beer. Welcome. That's all from my side. Back to Bodo.
Thank you, Eugen. Mrinal, it's your turn now. You're on semi.
Okay,
Here we go.
thank you, Bodo, for the opportunity. So I'd like to discuss onsemi's contribution to enabling this, what I call the golden era of semiconductors. There are so many viable choices on multiple semiconductor platforms, and our goal at onsemi is to deliver those platforms to you so they're usable, manufacturable, and ready to actually change and impact the world. So to begin with, for those of you who don't know, onsemi is a spin-off of Motorola's Semiconductor Components division that was based out of Arizona. Main thing to note is that we have held a very prominent position in the industry in enabling these technologies. And as you can see, we did $8 billion in revenue last year, of which over $800 million came from our silicon carbide devices. It's a very strong position, number 2 amongst the supplier world. And it also represents a very strong growth in this market as well. So everyone is aware that silicon carbide is growing very rapidly at onsemi through what we're doing in our interaction and enablement of these technologies. We're able to grow at twice that rate that the general silicon carbide industry is going. So a very strong position there. It's a testament to the success of what we're doing to enable these technologies for our customers. Getting into the technology, we've characterized and benchmarked our latest technologies against the competition. And I've tried to make this as easy as possible. So basically, I made it simple, 2 columns, one for conduction losses and the other for switching losses. And I've normalized it to the performance of our latest planar technologies. And what you can see from conduction loss perspective, we are at least 5%, if not more, better than the rest of the technologies out there. And from a switching loss perspective, it's even a larger gap. And the way we're doing this is a shrinking of that unit cell, as I'm showing there, where as you can shrink the unit cells, you can put more of these cells in parallel and derive a lower RDS(on) at the terminals. And in addition to that, we are innovating inside of these unit cells to deliver better switching characteristics than what you get simply from the capacitive effects of the device. So all of this is getting put in via innovation to deliver this industry-leading type of performance that I'm showing here. But performance isn't everything, as was well explained by the previous speaker. You also have to meet the reliability standards of the market. So these technologies are now going into very sensitive markets such as automotive, and there the standards are very, very high. And in automotive, they want to avoid field failures as much as possible. That imposes upon us, the semiconductor supplier, to assure very low PPM failure rates. So this plot is showing typically the most sensitive part of a power MOSFET is the gate oxide. And this is showing the lifetime of that gate oxide under these operating conditions. So typically our devices are operated at 18 volts. And you can see that at 18 volts, the lifetime of this under 20 years produces a PPM rate that's under 1. So we're talking about parts per billion type of failure rates of the gate oxide itself. So this is the type of quality that's required to meet the demands of such a high volume industry such as automotive. And so the lifetime and the failure rates are very, very good, but then the next question is, can these devices operate in a very stable manner through the life of these parts? And that's the next set of data that I'd like to show. This is a test of the stability of the threshold voltage. So the threshold voltage is the most sensitive parameter within the MOSFET. So it's going to change much more rapidly than one would see in RDS(on) or leakage or other terminal parameters. So we're monitoring the most sensitive parameter, which is the threshold voltage. And on the x-axis there, it's the number of switching cycles on the gate. So how many times it turns on and turns off. And what we see in the literature that in an automotive mission profile, it's about 1 × 10⁻11 cycles. And it's about 2 decades higher, or 2 orders of magnitude higher for industrial. And when you factor this in, you can see the stability of our devices are quite good. This is a testament of all the work that's gone into the engineering of the gate oxide to form such stable devices. In the mission profile of both of these different applications, you can see that our threshold voltage is quite stable, only 50 millivolts of shift in the course of the lifetime of these parts. So very, very stable operations as well, along with the long lifetime, low PPM rates. This entirety of quality that's required on top of the performance that you have to deliver as well. Okay, so moving on. At onsemi, I also want to note that we talk a lot about silicon carbide, but we have excellent silicon technologies as well. Both technologies are built on a vertically integrated platform. It gives us a lot of capability to not only deliver supply assurance, but it also gives us the ability to innovate at all of these steps and derive unique customized solutions for our customers. So we are heading into this golden era, as I commented before. onsemi stands here as a partner to enable the new ideas coming out of system designers and architects and make them feasible and manufacturable through the entirety of what we have to offer. Power devices, gate drivers, controllers, sensors. You can build the entire system with it on onsemi, and we also have a system team to assist our customers to help achieving their very ambitious design targets. And finally, I want to end with some tools that we have available online. So we have a very powerful simulator tool that's online. It's based off of Plex, and it gives you a simulation of our released products that are in the market. And what's really nice about this is that in addition to the typical performance that any model or simulator will give, our models also have the corners simulated as well. So you don't have to do an inverter simulation and guess via Monte Carlo what the worst case would be. This is already baked into the corner data that's being fed into the models here as well. And then you can take this platform and utilize the self-service Plex model generator. What that does is our customers can come in and create their own circuits, putting in their own parasitics, have a very high fidelity Plex model into which you can drop in all of our product solutions. So it gives our customers the opportunity to iterate their system solutions in the virtual realm before you have to commit to hardware. So this is a very nice way to accelerate their time to market on their advanced system level designs. So with that, I would like to conclude. Thank you again, Bodo. I appreciate the time.
Thank you, Mrinal.
And we welcome everyone to our booth, Hall 9, number 332, where we'd love to carry these discussions on further. Thank you.
It's Christian Reuter now from Fuji. Christian, here we go.
I use the time to say good morning to everyone already, because we need to speed up, I guess. And my name is Christian Reuter. I'm an application engineer at Fuji Electric. Thank you. And we heard a lot of SiC technology. I want to show you now how to use it. We have a module now with 2.3 kV, and it's a 1,200 amp module. I will show you a little bit how to use it. It's an HPNC package developed from Fuji Electric. So here you can see the module. I guess it's familiar. It's a half bridge. It's all chip and module. It's all from Fuji Electric. So as you can see, we have our latest SiC technology. We have the trench technology, what we also heard before from some other companies. That's what we use. We have a low RDS on, and so we can also have thinner layers, which helps, and finer cell pitch. So the advantage you will see, because we raise the high voltage, and later on you see an example. And very nice is that we don't need the freewheeling diode, so we have the internal body diode which can be used. It allows us to put more power into the module, which also benefits later on in the use case. The package, as you can see, the HPNC package here, so 2.5 bridge, very low strain inductance, because we have laminated bus bars inside. This helps a lot. Then the auxiliary terminals here, these are the stubs, which is quite easy to mount your driver circuit board. And then also the module from the structure itself, from the connectors, it's very easy to parallel, what you also will see later in the next slides. Then the 1,500 volts is something high demand from the market. That's why we developed the 2,300 volt devices. So a typical use case is the renewable energy, like the photovoltaic industry, the renewable with wind power. Then we see more interest from the electrolyzers. Maybe someone else saw another presentation this morning where they just sold frequently 1,500 volts. Then the battery storage systems, and also maybe in the future for the charging for the very load heavy for megawatt chargers for trucks and so on. So a little bit about the module itself. So, or why we did. Typically using 3-level topology, as you can see here, but with a 2-level topology, we can save space, you will see later on, and also reduce the voltage drop here. And this also helps to reduce the power losses. Sounds logical. So here you see it from the MOSFET compared to the IGBT, and this one is from the diode side. So then we have an example where we tested 1,500 amps rate voltage and 1,200 amps. You'll see the result for turning off. And interesting is when you switch it off. So first, also a nice switching behavior. And when we the spike, here you can see we have 2,000 volts. So perfect part of with a 2,300 volt technology, absolutely perfect for the 1,500 volt applications. And now you will see the advantage because you're using SiC compared to the old IGBT technology. So as you saw before, the circuit, you see here, it was solved with 3 prime pack modules, 1,800 amp, 1,200 volt modules. So you need a lot of space. If you want to build a full application, you need 18 prime pack modules. Quite a lot, also quite expensive. So, and if you can reduce the same amount to a 2-level version, then you to get the same power. We did it with 2.3 megawatt. So it could be a big solar park, for example. And then you see that you only need 9 HPNC modules. Benefits, so we reduced the power losses, what we saw before. Then reduction of the footprint, which is quite easy to see. And footprint is only 68%. Then with a high switching frequency, also the passive components. You can't see here, but I guess all the engineers will understand easily. So benefits looks like this. So it was space, and these are the power losses. Also from 17.2 kilowatt are reduced to 15 kilowatt. That also helps me to reduce the heatsink in general. Not only the space I need, so also heatsink will be reduced in addition to the passive. Then we had 2 kilohertz switching frequency here for the 18 prime packs. And now we reach we test with 4 kilohertz switching frequency for the HPNC with the SiC technology. Details you can see below or later when on our booth. I guess not everybody can read. So to summarize a little bit, as I mentioned, ideal solution for 1500 volt applications. Easy paralleling because of the structure of the module, this with a package. And this fits perfect in any application when you want to switch from a 3-level to a 2-level and reach the 1500 volt. So less complex, also from the connection itself. Very high density of the application, reduce the number of modules as you learned, and also the gate driver and all in addition what I need, so this helps also a lot. Then 13% reduction in power losses, which I mentioned with a heatsink, and then the absolute smaller footprint. And very important is, if you need to talk to your salesperson, size and cost reduction in the system. And then I want to say thank you, our booth is quite close. Arigatou gozaimasu.
Now it's Pierre from CISSOID. Pierre, it's your turn.
Hello, good morning. So my name is Pierre Delatte and I am CTO at CISSOID. So I will discuss how SiC inverter control module can accelerate the design of efficient motor drives. Beside passenger car, a lot of industries are today moving to electrification, which is the only path for net zero emissions. And this includes trucks, EV machines, autonomous vehicles, and even electric boats and e-aviations. But these industries are facing new challenges moving to electrification. First, they have to deal with new technologies, which can be electric motors, but also new power semiconductors technologies like silicon carbide and gallium nitride. They also would like to have one inverter platform meeting different requirements, so they need a modular solution, either in terms of power or voltage. They are coming with specific requirements in terms of housing, also motor control. Each industries has specific EMC and safety requirements. We see also a lot of applications operating in extreme environments, especially temperature and vibrations, but still everybody wants to get a short time to market. And finally, the supply chain in the electronic industry is still tight. So to address these challenges, we are offering a modular hardware and software solution to accelerate the design of SiC inverters for electric drive applications. So the core of our technology is this SiC inverter control module, which is combining a power module, a gate driver board, but also a control board. The control board is based on silicon mobility microprocessors and also running their software, which is optimized for electric motor control. For rapid evaluation in front of a motor or on a motor bench, we are offering reference designs, designed for operation at 800 volts, and with different solutions, benchtop for benchtop testing or for onboard field testing. So regarding the hardware, so the hardware is based on a SiC intelligent power module, which is modular in terms of current, offering the low switching energies of silicon carbide. And together with the power module, we've integrated a robust gate driver against high DVDT and high common mode currents, including all the faults you need to safely drive silicon carbide transistors. So we have a solution fully optimized for silicon carbide, including for short circuit. Together with this power module, we have a companion capacitors with very low ESL. And so thanks to that, you get a fully characterized switching loop, which is optimized for optimal switching at 800 volts. And finally, the control board rely on the T222 microprocessor from Silicon Mobility, which is now part of Intel. So it includes a dual-core ARM together with FPGA functions, which is very useful to implement fast control loops, but also for a fast reaction to faults, which is supporting functional safety up to ASIL-D levels. So regarding the software, the OLEA app inverter software from Silicon Mobility is highly configurable and optimized for motor control for different types of motors. It implements advanced algorithms, including field-oriented control, frequency scaling, SVPWM and DPWM modulation up to 50 kHz. Short dead time compensation. So we are publishing this month papers demonstrating 4% of THD reduction thanks to this algorithms. And also we support flux weakening management. And the software has been also certified for functional safety ASIL-D level. And so finally, to support customers in their inverter design, we offer two reference designs. So a first one for benchtop testing and a more compact solution for onboard testing. This reference design includes additional functions like EMI filters, the current sensors, also a function for passive discharge, and we've demonstrated power efficiency in excess of 99%, sorry. And for benchtop testing, the solution is also providing a high-speed Lauterbach interface, which is used for debug and calibration. And the solution offers very good power density performance. So thank you for your attention, and you can meet us on booth 6222 in 09 if you're interested to know more about our technology. Thank you.
Thank you, Pierre. It's now Ramanan from Qorvo.
Thank you very much for having me here, Bodo, and good afternoon, everyone. While we get set up here, I'm going to tell you a story. A senior sales executive in our company, Qorvo, lives in beautiful San Diego, California. Lovely beaches, blue skies, blue ocean, and nice warm weather, 20 degrees centigrade all through the year. He tells me that the electric utility company contacted him last year and gave him a very low rate for the electricity consumption in his home under one condition. That condition was if he will allow the utility company to be able to turn off some high energy consumption appliances in his home on days when the grid is oversubscribed. Ladies and gentlemen, what we are seeing play out in front of us here is called dynamic load management. The electricity grid all around the world is getting fast oversubscribed. Power-hungry EV charging stations, cryptocurrency mining machines, Bitcoin mining machines, and all of these things are really putting a load on the grid, and the grid is not going to be able to keep up in the near term. And what's going to relieve this is having the ability for both the consumers and the utilities to manage the load on the grid by selectively disabling equipment which consume lots of power from it. And that's going to be enabled by semiconductor circuit breakers, which is the topic of my discussion here today. There is a tremendous amount of activity happening around the world today in semiconductor circuit breakers. These are fundamentally more reliable. They don't suffer from arcing and failures related to arcing. They have much faster reaction time, so they can limit the current, overcurrent, before they actually turn off. That's a big advantage which they bring. But most importantly, when you add these semiconductor devices to connect and disconnect loads, it gives you enough of a critical mass of semiconductors there to now be able to do additional management. You can add wireless connectivity. You can add metrology and monitoring. So it really gives you the capability to remotely disable and enable these equipment, which is taking the power from the grid. And standards are fast emerging, both in US and Europe, to enable the commercialization and deployment of solid-state semiconductor circuit breakers. So the semiconductor circuit breaker, what does it actually look like? It's actually going to be very similar looking to the electromechanical circuit breaker, which is installed in your circuit panel in the wall in your home. It is in a location where there's very little airflow. It's highly space constrained. And if it's located in a place like Texas, where I'm from, the garage is going to be 40 degrees centigrade temperature in the peak of summer. So what you really need are components there which are very efficient. They dissipate very little power when they're conducting the current. And you need to be able to fit them all in a very small size with the additional components that will allow you to do the remote management and wireless connectivity and things like that. And finally, these devices are circuit protection devices. In the normal operation and even in the overload conditions, they're supposed to be non-interfering with the consumption of electricity. But in those extreme situations where the current levels go 5 times or 10 times higher than the nominal use case, they need to be able to react fast and shut things off. So the FET needs to be able to provide a very high peak current capability. Okay. So silicon carbide technology is in the center of all of this because silicon carbide enables you to achieve much, much lower on resistances in a high voltage switch in these standard, industry standard packages than what silicon would allow. You would have to parallel lots of silicon devices to achieve a certain low on resistance, but you could do that with fewer devices with a silicon carbide device. And you're all very familiar with silicon carbide power MOSFET technology. Several suppliers in our show here today offer silicon carbide power MOSFET technology. But today I'm going to tell you about an alternate technology, which is called the JFET, or the Junction Field Effect Transistor technology, which is from Qorvo. Our company, Qorvo, has been commercializing and manufacturing silicon carbide JFETs for more than 10 years now. We offer the products to be used in regular switch mode power supply applications, as well as in these kind of circuit protection applications. And this silicon carbide JFET technology is fundamentally slightly different from MOSFETs. And if you compare the structure of the MOSFET on the left-hand side and the JFET on the right-hand side, there are two things really which stand out. The first thing is, if you look at the different component of the resistances, from the source up on top to the drain on the bottom, you have the resistance of the native silicon carbide region and the drift regions. But look at the MOSFETs. They have this additional channel resistance. This is the artificially created channel of electrons and accumulation layer when you apply a positive voltage on the gate. But over there on the right-hand side, in the JFET technology, you actually don't see a channel. Okay? So these are normally on devices, and there is normally a connection from the drain to the source. And you'd have to apply a voltage to the gate to turn off the device by creating a depletion region. So the lack of this channel component, which can be a pretty substantial component of the total resistance of power MOSFETs, that channel resistance component is missing, is not there in the JFET structure. As a result, within the same given chip size, you're able to achieve much lower resistances with the silicon carbide JFET technology. What that means is in an industry standard package, we can offer a much lower on resistance with the JFET technology than a power MOSFET technology. The second thing from a reliability perspective, you notice that the gate oxide, the blue layer in the power MOSFET, is completely absent in the JFET. Okay? And that relieves some complex engineering, which was spoken about earlier in power MOSFET technology. It relieves all the trouble with the JFETs. And this gives better reliability, especially after catastrophic events like avalanche switching or short circuits, where things like threshold voltage changes or on resistance drift is completely not a concern in the JFET technology. So my conclusion here is the JFET technology is a uniquely advantageous technology for these applications where you really want high reliability, long lifetime, and ultra low on resistance. So at the show here today, in PCIM 2024, Qorvo has announced the industry's lowest on-resistance power device at 750 volt rating. It's a 4 milliohm JFET in the TOLL package. It's on display in our booth right here in this hall, so please do come by and see us. And this device is squarely targeted at these circuit protection applications. So if you compare any semiconductor technology, GaN or silicon carbide, in a toll package, and you look at the lowest on resistance available, Qorvo is almost 3 times better than the closest competition. And then the peak current capability. The saturation current of our 4 milliohm JFET is close to 600 amps. What that means is in a circuit protection application, it can allow you to take the current up to 600 amps without saturating and immediately enforce a turnoff. And finally, one of the unique aspects of the JFET technology is a PN junction, which is on the gate to source of the device. And the PN junction's forward voltage is a very nice source to recognize the temperature of the device. So in these applications where you really want to monitor the temperature of the critical power switch component, you could use the forward drop of the gate to source diode to actually do some sensing of the temperature, in situ native sensing while the device is operating. So lots of cool things about the JFET technology. We hope I have spiked your curiosity here. Come by our booth and talk to us, and we'll be happy to educate you about alternatives to power MOSFETs in the world of silicon carbide. Thank you.
Thank you, Ramanan. Now we continue with Carlos Silva from WeEn. Carlos, it's your turn.
Thank you, Bodo. Good afternoon, everyone. Thank you. So today's presentation is going to be about silicon carbide. I'm going to give you a brief introduction about our company, who we are, and also what we are doing with silicon carbide to really help engineers to solve the challenges they face. So our company has a humble background from the 1950s back to Philips times. We became an independent company in 2015, and ever since then we've been introducing more devices. Philips was very big in home appliances, and we have been increasing our product range to also cover industrial and automotive applications. When you talk about the expansion of the technology, you can see here that the wafer sizes have been increasing, the device sizes have been going down. At the present, we are working on 6-inch wafer. We are also planning to go into 8-inch very soon. You can see we have a very big portfolio covering not just silicon carbide, but also other semiconductor devices. SiC, normally when you think about SiC, the idea that the media and the industry gives you is all about automotive. Actually, there's quite a lot more to silicon carbide than automotive. We're going to see this in the coming few years. We're just about harvesting the technology of SiC, leading a little bit in what was before silicon. There's still a lot more potential for silicon carbide to grow. It's going to be mission critical applications in the air, in the sea, mining machinery, etc. And then this slide in here, I'm showing what we are doing really to improve the technology. As you can see, this was our first generation of silicon carbide MOSFET. What we're doing really is reducing the size of the cell to reduce the thermal dissipation. Each of these layers adds thermal resistivity, so the device is not really able to dissipate thermal energy. And on the other side, you also have the fact that it also has a higher resistivity, so you have more losses. So they don't really help each other. So what we're really doing is reducing these to be able to have a better thermal dissipation. Now, this is the biggest challenge for SiC applications, because what you see is that as power density is really the key for silicon carbide, getting the devices smaller, getting the devices more efficient, and really what we're doing here is trying to accommodate for less losses. But not also on the silicon, we're also working a little bit packaging level. You can see here that silicon devices were typically welded to the chip, and you can see the layer of solder. And this layer was okay for silicon because you only really go to 175 degrees, 150 degrees. But with silicon carbide, actually the chip can withstand temperatures much higher than that. It can go up to 200 degrees. And so what we're doing is we're leveraging the use of sintering to be able to increase those temperatures and really improve the power density of the converters. Here you can see also innovations in terms of packaging. We have traditional surface mount packages which you would use, and now we are also introducing topside cooling packages. Now the advantage with this is when you have a heatsink, when you use the PCB as a heatsink, you have all these layers of thermal resistivity which are really making the junction temperature is actually hotter than your heatsink temperature. And so by leveraging new package innovations, what we're doing is we have a topside cooled package. The package is assembled on the PCB. It doesn't transfer the heat directly to the PCB, which increases reliability because the components next to it are not getting so hot. And then the heat dissipation can go straight into the heatsink. So the device will run cooler. You have increased reliability. So these are some of the products that we have. As you can see, anything covering from standard TO to 20 packages, all the way to modules. We have our own module plans, so we're able to customize these modules to the customer needs. We have full silicon carbide modules, IGBT, hybrid, anything really in between we can make. This is all done in-house. And we also coming soon some new products. We just released the TOLT and the T-Pack topside cool devices, but we also have some other packages, exciting packages coming forward. And it's really a new world for silicon carbide and wide bandgap in general. We're just really starting to see the changes in the industry, and I think that the future is quite exciting for the technology and for engineering in general. So thank you so much. Come and see us. We're in Hall 9, booth 538. My name is Carlos. I'm part of the engineering team, but we also have sales, and our CEO is also with us. So feel free to come and join us and ask any questions that you may have. Thank you.
Thank you, Carlos. It's Stefan's turn. Stefan represents the Semikron Danfoss, something between north and south of Germany.
That's correct. We combine both sides of Germany, the best ones, of course. I was looking at let's maybe start with that combination first. So Semikron Danfoss, relatively young company, 2 years, not even 2 years, but 70 years of packaging experience. How does that happen? Well, easy. We have been founded as a merger of Semikron here in Nuremberg and Danfoss Silicon Power in Flensburg. This brings a lot of experience together. We are quite a big company. We did more than €1 billion of turnover last year. We have more than 4,000 people. We are spread all over the world with factories as well as with sales offices. We like to be close to our customers. And that makes us the largest chip-independent manufacturer of power modules in the world. That's something we are proud about. I was looking at the title that Bodo gave this forum here, The Future of Power Electronics. And for some reason, I looked at it and I thought first, is it a question or is it a statement? So I took it as a question and I said, is it really the power, silicon carbide? Or is it really the future? Yesterday, I heard the term on this stage about electrify everything. And this is exactly the time we are living in today. Everything becomes electrified. It's combustion engines that are replaced with electronics. It's hydraulics that is replaced with electronics. So everything electrifies. Why do we do that? Because we want to decarbonize. Very, very clear target. But it also means we need a lot more electrical energy than we have today in the future. It would be a shame if we created like that. So it's also clear if we want to be green, if we want to be decarbonized, we do not need only on the load side, we also need it on the supply side. So of course, green energy is the target. The nice thing for us power electronic guys here is you need power electronics for all of this. So that's beautiful. But you need it also very, very efficiently because you want to get the most out of the energy you harvest. And you also want to use as little energy or waste as little energy as possible. So it helps not only in the energy itself, it helps also in the value chain completely. If you have less losses, you have a smaller heat sink. We heard that already from the colleague from Fuji. That saves also CO2 and decarbonizes if you need only half the size of a heat sink. So in other words, yes, silicon carbide is definitely the future of power. And I want to give you an example, which is somewhere in between the generation and the consumption. That's energy storage. Super important part. Because the wind will not always blow, the sun will not always shine, so you need something to store your power intermediately in these times. The chart you see on the right-hand side is from Bloomberg. They basically say this year there will be an addition of 50 gigawatt of energy storage power installed this year in the world, and by 2029 this goes up to 100 gigawatt every year. So that's huge. So you have to be very much to the point with this kind of technologies. So I brought you one example on how to equip actually power electronic for battery energy storage, and we did a comparison. 1500 volt. We also heard that before is important. It's the solar voltage. That's the energy storage voltage that is used today. And if you look at around about 1 megawatt, 1.2 megawatt converter, you have different options how to get there. One is you have a Semiconductors 10, that's what we call it, TNPC topology. You see two modules. You need a vertical, which is in this case a 2300 volt module, and you need a horizontal, which is a 1200 volt module. And with this you can reach 1.2 megawatt roughly. You also generate losses here, and that's incredible, almost 14 kilowatt of power losses when this thing is running in full load. And if you look at the mounting space you need, roughly you push 900 watts of power through the mounting space that you have, that's per square centimeter. Another option to increase the efficiency would be ANPC topologies, active neutral point clamp. So you need a few more modules because now you have suddenly 6 switches that you need per phase. You still run at a relatively high power, megawatt. You have roughly 10 kilowatt of losses, so you save already about 40%. But unfortunately, you need a bit more space. So you go up to down to 800 watts per square centimeter only on power that you can push through this kind of mounting area. So what is the solution? It's of course silicon carbide. What else? So we have also a higher voltage rating now in our Semigens 20 package. That's a 2 kilovolt silicon carbide MOSFET half bridge. It comes with a 1700 amps of nominal current. And if you use this one, it's pretty obvious you only need 6 switches because that's all what it takes to get to 3 phases. The losses go down to 7.5 kilowatt and the density basically 2.4 kilowatt per square centimeter. So you become smaller because you have a higher power density, you become more efficient, you save on the losses. You will save on the housing that you need for the converter. You will save on the heatsink, of course. Overall, it's a big saving and brings a real benefit to this application, as well as for solar, as well as for wind power, as well as for hydrogen. So yeah, silicon carbide again is the future. Just some words. How do we do that? In this very special case, we are using also a sintering, as the colleague from WeEn also mentioned. We have a sinter die, we have different bond wire technologies that we can utilize. Of course, we're also using a better substrate. It's not the standard aluminum oxide. We are using silicon nitride in that package. So we try to get all the technologies that are suitable for a certain application and package into that one. Besides that, we do not only have industry standard packages, we also have the automotive packages, also higher integrated products. We also have that 2 kV chip in an IPM module, also for high power. And we have the partnerships. We are chip independent, I said that, and this chart on the top right, you see all the different chip partners that we work with, not only silicon carbide, but also in the silicon world. And with this, I would like to conclude. If you want to talk more, there's a big red bar over there on the top. That's our booth. Just come over and let's have a discussion. Thank you very much.